Hello everyone. Hope you guys are doing great. Welcome to CiscoLive 2024.
And welcome to our session.
My name is Vinay Sawant.
And I'm Christian Soto, and we are very happy and excited to present all of you with our session today, NXOS Troubleshooting, expanding your tool set with feature-rich NXOS.
In this session, we are going to present you various troubleshooting tools available on Nexus 9000. We are going to present you one tool at a time, going to show you how to use it, when to use it, with some troubleshooting examples. But before we begin, we would like to give you a brief introduction about ourselves. Again, my name is Vinay Sawant. I am currently working as escalation engineer for data center routing and switching team at RTP North Carolina. As part of my everyday work, I provide escalation support to my team members, customers, and partners. Apart from that, I provide training, provide mentoring, and write technical documentation. Well, that's about me in brief. Christian?
Once again, my name is Christian Soto. I'm a technical consulting engineer that works with both the data center routing and switching team, as well as the data center software team, helping to bring all of your solutions to success from our routing and switching platforms all the way to our various data center applications. Working with both teams, I serve as a mentor to assist with training and to create internal and external documentation, not only to make all of our experiences in TAC better, but to also make all of your experiences with TAC better. And so without any further delay, let's begin our session. Let's go beyond.
All right, we are going to talk about these troubleshooting tools today. We are going to start with Ethanalyzer, span to CPU, ELAM, consistency checker, show troubleshoot, and iCAM. Today we want to give you as much information as possible. So what we have done, we have kept the question and answer session at the end of our session. So as we go, if you have any questions, please note them down, and we're very happy to answer all your questions at the end. So let's begin with our session. For the purpose of today's discussion, we are going to use this simple network topology diagram. What we have here is host 1 connected to leaf 1, leaf 1 connected to spine 1, spine 1 connected to leaf 2, and host 2 connected to leaf 2. Let's begin with our first tool, Ethanalyzer. Ethanalyzer is the tool that helps us capture the traffic going to and from the CPU of Nexus 9000 suite. The command syntax is Ethanalyzer local interface. Interface you want to capture on, display filter or capture filter, limit capture frames, and write to boot flash. The interfaces which you can capture on are in-band, management, front panel ports, or management port. The display filter means capture everything but only display what I'm asking for. Capture filter means only capture what I'm asking for. Limit capture frame 0 means unlimited capture. Limit capture frames 100 means it will start after 100 frames capture. Write option helps us save the file to boot flash. We are going to talk about remaining options in upcoming slides. In the first example use case, imagine host 1 is trying to ping the default gateway, and you want to verify if their ICMP request is reaching the gateway and if they are responding with the ICMP reply. What we see here is ICMP request is received and ICMP reply is generated. I use Ethanalyzer with the filter ICMP, and I can see the packet. What if you wanted to verify where is this ICMP reply sent out? We can use Ethanalyzer with the option decode internal. Like in this case, this ICMP request is sent out on destination port 17, which maps to front panel port Ethernet 1.1. I use the command show interface hardware mapping to find that. Let's say if you didn't see ICMP request and reply, the next obvious thing we all do is check for ARP request and reply. To verify if ARP request is making up to the gateway, we can use Ethanalyzer with the filter ARP. And like in this case, we can see ARP request is received and ARP reply is generated. The only problem with the filter is if you run this filter in your live production network, you're going to see a lot of ARP requests, and it's going to be difficult for you to identify where is my request. For that purpose, we have some more interesting filters like arp.src.proto, which is capture the R based on source IP address, or arp.dst.proto, which is capture the R based on the target IP address. With this, you're only going to see what you want to see. Moving on to our next example use case. In this case, host 1 is trying to communicate with host 2. And let's say they're observing slow download speed or application slowness or application timeout. We all get this kind of problem every now and then. What we do in those kind of cases, we check all the devices along the path for CRC errors, input discards, output discards, or any QoS congestion. Or also we check the devices for any link flap or any hardware instability. One of the other important things we should check if this flow is getting software switched. To verify, you can run Ethanalyzer on leaf 1, spine 1, or leaf 2. The expected result is you should not see any output because the communication between host 1 and host 2 is done in hardware. Ethanalyzer can only capture the traffic punted to CPU. So if you see the output with Ethanalyzer, like we see in this case, this is not a good output. It's a pass-through flow. You should not see anything. If it is getting punted to CPU, which we call as a software switching, we have some upcoming slides where we show how to troubleshoot those examples. Let's move on to our next example use case. In this case, we are using Ethanalyzer to troubleshoot routing protocol adjacency between Nexus and the adjacent device. In this case, I'm running an Ethanalyzer with the filter BGP source IP and the BGP peer IP. What we see in this case is SYN, SYNAC, ACK, exchange, and finally we see BGP update packet exchange. This is a good working example. Now let me show you a non-working example. I remember a case I worked with one of my customers. They called us saying, hey, my BGP between Nexus and firewall is not coming up. It was up, but this link flat. The link is okay now, but BGP is not coming up. So I went on call with the customer. I verified their BGP configuration was okay. I verified the link along the path. I pinged the BGP peer. It was all okay. At that point, I decided to use Ethanalyzer. And what I see, SYN, SYNAC, ACK packets were exchanged, but BGP update packet was getting retransmitted. So that tells some device along the path was dropping the BGP update packet. So at that point, I decided to ping the BGP peer with a higher packet size and don't fragment bit set. With that, I saw the ping was failing, which means a bigger size packet is not going through. So I decided to go again and check if there is some device along the path configured with smaller MTU. And there you go. There was the one device configured with smaller MTU, 1500. I bumped it to 9216, BGP came up. So what was happening in this case was when this customer configured BGP 2 years back, they were having less number of prefixes to exchange. Hence, that time the BGP update packet built was the smaller size. Now, over the period of time, their BGP updates and routes grow. Now, when the BGP was coming up, based on the negotiated MTU value 9216, Nexus tried to build a bigger BGP update packet, and it tried to send, but the device along the path could not handle it, and it was dropping. The moment we increased the MTU, BGP came up. So how Ethanalyzer helped me in this case? It helped me showing there is some packet dropping. It gave me a clue where to check. Let's move on to the next example use case using Ethanalyzer to troubleshoot control plane related problem. We have control plane protection at Nexus CPU level. We call it COP. We all get ARP broadcast storm or sometimes ICMP, unwanted ICMP, or there is some misbehaving or newly configured server sending some unwanted traffic, or there is some ARP scan, virus scan going on. In those cases, what happens is that traffic comes to the CPU, Nexus control plane gets congestion, and what we start seeing is control plane protocol like spanning tree, UDLD, BFD, BGP, or any other routing protocols, they will start flapping. So what we do in those kind of cases, we run a command, show policy map interface control plane, and we look for what class has a drop. Let's say if you see drop in ICMP class, you know you run Ethanalyzer with the filter ICMP, and you can see which ICMP excessive traffic, who is sending that traffic. Same thing with R. If you saw a drop in the R class, you use the filter with R. But there are some classes like this class, which is L3UC data. You know it is matching glean traffic, but you don't know what is that glean traffic. Let me show you how to find that. What you do, you grab the class name, go to the next page, and say, show system internal access list, COP stats, stage 1, pipe include the class name. From there, you find out the queue number, and then run the Ethanalyzer based on the filter cisco.blob.soup_queue number, and there you go, it will show you the traffic. Some other things we can do with Ethanalyzer is write the output to the boot flash, or capture multiple files using ring capture frames buffer, or we can also read the saved capture locally using Ethanalyzer local read option. Well, that is about Ethanalyzer. Let's move on to our next tool, span to CPU. Imagine you want to capture a traffic between host 1 and host 2. Ethanalyzer cannot help us to capture that traffic. What we do in those kind of cases, we use local span or we use ER span. But both those tools need a PC connected or a server connected, or you want to send somebody to data center to connect it. That can take time. But span to CPU can help us. What this tool does, as the traffic comes in, is going to redirect your traffic to CPU, and then using Ethanalyzer, you can capture the traffic. This redirection is done in hardware. By default, we can only capture 50 packets per second. You can use filters like VLAN or access list. Let me show you how to configure that tool. You say config T, monitor station 1, source interface, the interface you want to capture on, destination interface, soup is 0, which is a supervisor. You apply the filter if you want, based on access list or VLAN, and then run the Ethanalyzer with the keyword mirror. That keyword is important to see that traffic. In this case, we can see that traffic using Ethanalyzer. But what if Ethanalyzer or span to CPU is not helping in the particular use case scenario what you are troubleshooting? In those cases, Christian has some more tool for us today. Christian, you want to go?
Absolutely, Vinay. Thank you very much. Like Vinay said, whenever you have a scenario where the traffic isn't being punted to the CPU, or it's not being seen as pass-through traffic in span to CPU, what tool can you use? Where do you go to figure out what the switch is receiving and how we're forwarding it? In that case, you can use our third tool, the ELAM, also known as the Embedded Logic Analyzer module. This packet capture tool takes a single packet coming in on ingress to the switch, either directly to its CPU or through it in the data plane, and from there determines the forwarding decision. Because we have to determine that forwarding decision, we have to take this packet capture very close to the wire at the ASIC level. And the specificity of this capture means that it is only supported on cloud scale Nexus 9Ks, not first generation or R series Nexus 9Ks. That said, the syntax for ELAM is fairly simple and can be broken down into 5 general steps. The first of which is defining your debug. The second, defining the trigger at the ASIC. The third, setting the flow that you want to trigger for at the ASIC. And the fourth is to start the capture once you're ready. Once the packet, or you believe that the packet has arrived at the switch, you can then report on it in order to get the particular report for the ELAM. And one of the scenarios where we use the ELAM is a very common one where you're trying to ping your gateway to determine if this gateway is both receiving your traffic and if it's processing it correctly. So what we want to do in this case is start with a debug platform internal TA ELAM. And from there, in this case, we may not necessarily know where our traffic might be arriving, right? So we can run this capture to be wide open with a trig in it. From there, we define it for the particular flow that we want, from host 1 to leaf 1, our gateway, and then start it once we're ready. After we believe that we've received the flow, we report on it, and we get the following output. we can see that in this case, our traffic is arriving on Ethernet 1.1, our expected source interface, in the expected source VLAN, VLAN 10. But note how there's a little bit something weird with the outgoing interface, right? You can see that our DMOD and DPID values are 0. Well, what does it actually mean? How does that correlate to what we're actually seeing? Well, if you think about it, because the traffic is destined directly to us, that means that there is no end destination beyond us. We are it. And so we must process it at the CPU. Hence why we have a supervisor hit and supervisor index. We can then decode this supervisor index using this command in order to figure out how the Nexus 9K is processing this traffic. From what we can see here, like Vinay explained earlier, we will process that ICMP packet in the ICMP COP class, and therefore that shows us that we are receiving that traffic and processing it as we would expect. But what if, like in our next scenario, we're not the end destination ourselves at the gateway? We're trying to forward it somewhere else, as if we're the core switch or the interconnect in between two ISPs. And so we want to verify that at that specific interface on our switch, that we're receiving the traffic and forwarding it in the expected manner. In which case, the first thing we want to do is verify the information for the interface where we believe we should receive that traffic. Hence, Ethernet 1.1 in this case on our source leaf. We can use the command shown here on the screen in order to get the slice number and source ID at the ASIC level. We'll also want to keep in mind in this case that our flow is unencapsulated, such that when we actually run the syntax for the ELAM, it will start with the same debug, but our trigger at the ASIC this time will include trig in it, the particular slice number for that interface, in select 6, which indicates the outer IPv4 header of our flow, and then the source ID corresponding to that specific interface. We then set the flow and start it as we would expect, and once we report on it, we can look a little bit more closely at our report this time. Notice how the slice number is our expected slice, and we have the expected incoming interface and VLAN. But our outgoing interface now, since we're not the final destination, actually shows values for the DMOD and DPID. In which case, to figure out what interface that is, we'll just want to take note of those values, and we can run the same command that we ran for Ethernet 1.1, just instead filtering for that specific DPID value we found from the report. And we can see, once we filter for that value, that it corresponds to Ethernet 147, which in this case is our CDP neighborship with the spine, showing that we're receiving that traffic and forwarding it on to the next hop as expected. Now, what if, like in Vinay's prior example, we're not even completing ICMP because we can't even resolve ARP, right? In that case, whether we run the capture wide open or for a specific interface, the general flow is going to be the same. Just that the major difference is that when you define that flow, you're going to do set, outer, ARP, the source IP address, and then the target IP address of your ARP packet. And so once you report on it, you'll see that the information that's presented is the same as before, except our outgoing interface is now DESPTR, or Destination Pointer 10. That means that we will be flooding this ARP packet on every interface where we would expect to be forwarding for VLAN 10. Now, because there are multiple ways to decode what interfaces we're flooding on, and there's a little bit more complexity involved, we've left that all for you as an exercise for the hidden slides. And now for our last example, one of our most common ones in the data center is using VXLAN, right? You want to confirm that from host 1 to host 2 that we're forwarding this packet end-to-end properly over our fabric, and that we're not dropping it or seeing any issues. In that case, once again, you can either run the capture wide open or for a specific interface. I chose in this particular example to run it for a specific interface. And with that in mind, we'll keep track of the specific interfaces where we want to notice that traffic. So Ethernet 1.1 on our source leaf and Ethernet 1.3 on our destination leaf. So that said, we run the same command from earlier to get the slice number and source ID of each of those interfaces. But there's a little bit of a snag this time, right? Because it's VXLAN. On our destination leaf, since that traffic is coming from the fabric, we are expecting that traffic to be encapsulated. So in that case, how do we actually account for that when we do the syntax for the ELAM? And so if you look on the left for our source leaf, everything is pretty much the same as before with the flow of syntax. But as you can see for the destination leaf on the right, that we're going to use inselect 9, which means that we will be triggering on the inner IPv4 header of our VXLAN flow. And when we define that flow that we want to trigger on, we do set inner IPv4 for that specific flow. Once we're ready, we can then report on it, and we see the following. On our source leaf, we're receiving it on the expected source interface and VLAN and sending it out somewhere on our layer 3 VNI. On our destination leaf, we are receiving it on the expected interface in the layer 3 VNI and sending it somewhere on our destination VLAN. Now, once again, in order to decode those interfaces, we just have to take note of those DMOD and DPID values from each one of the ELAMs. And from there, we can run that command from earlier with those DMOD and DPID values filtered to get our outgoing interfaces. On our source leaf, we're forwarding it on Ethernet 147, and on our destination leaf, we're forwarding it on Ethernet 1.2, showing that from source to destination in that direction, we are properly forwarding the packets as we would expect. Now, as we conclude with our ELAM session, we'll be concluding or continuing with Consistency Checker, our next tool. But I want to present you all with a little bit of a thought experiment as we do this. This is your network, let's say. You have 2 core Nexus 9Ks with a bunch of devices connected to them, all on VLAN 100. And you want to verify why in your specific environment, you're able to ping between some devices and others can't complete ICMP. Similarly, some can't even complete ARP. I want you all to think of the first thing in your mind that you would use to troubleshoot this type of problem in your network, and hold it there. And Vinay and I will show you some of the techniques that we thought of to troubleshoot this type of issue. So some of you may have thought to check the links between the core switches or to the devices that are connected to them. You may have also chosen to check for MAC learning or SCP forwarding for the appropriate VLAN, or even any core access lists that are present on the switches. But you would find that all of these come out clean. You may have also tested for different combinations of connectivity for different end devices, but there's no discernible pattern that you can find. This is where Vinay's troubleshooting techniques that we presented earlier in the session come in handy. Because using Vinay's software switching techniques with Ethanalyzer, you can see that there's no software switching happening on the core switches. So that means that we're not punting to the CPU and dropping it. Similarly, with the different ELAM techniques I showed you, you would be able to find that there is a discernible pattern between the hosts. Anything that appears to be working in any direction appears to be going over Ethernet 149. But anything that appears to fail in any given direction appears to be going over Ethernet 150. So knowing this and the fact that everything up to this point has otherwise come out clean, how do we take our troubleshooting to the next level to figure out what might be wrong with Ethernet 150? Where do we go from here? And this is where our next tool, the Consistency Checker, comes in. Because it takes that higher level software configuration that we ourselves have set on the switch and compares it to that lower level output at the ASIC hardware tables. This is a great command or series of commands to run in tandem with Ethanalyzer and ELAM, not only because it can be run for a wide variety of features, but it can capture things at a level that even those capture tools have a little bit of difficulty seeing. In this case, the way that we run Show Consistency Checker is with Show Consistency Checker, the feature we want to check for, what exact part of that feature we want to check the consistency with, and whether we want a brief or more detailed output. And using Consistency Checker as an example, we can see that by checking for the consistency for VLAN 100 on both core switches, that core Nexus 9K1 appears to have some kind of inconsistency with Ethernet 150, showing that perhaps the reason why we're seeing forwarding issues is because that VLAN isn't even being properly associated with that interface at the hardware level. We could have also gotten a similar output either by checking for the STP state or for the layer 2 switch port status of the port channel 100 between the core switches. But sometimes we need a little bit more context for what things are consistent and in a little bit more detail. So I believe Vinay has some other tools to help us see that.
Thanks for sharing this awesome tool, Christian. My favorite tool in consistency checker is show consistency checker VXLAN config check. It's going to go and check your VXLAN config and going to help you identify if there is something misconfiguration. VXLAN can be a complex technology, so this tool is very handy to help you identify the misconfiguration. Moving on to our fifth tool, show troubleshoot. Imagine you are troubleshooting a layer 2 flow or a layer 3 flow, and you use ELAM. It shows packet is either dropping or it is forwarded to the wrong interface. So you come back and verify your MAC table, verify your IP routing table, verify your ARP table. But remember, what you're checking is in software. That has to be pushed down to hardware. And sometimes when it pushed down to hardware, either it is not programmed properly or it is misprogrammed. So in those kind of cases, I remember I used to run a lot of commands to verify if my MAC is misprogramming hardware or a route is misprogramming hardware. To remember those commands, it can be difficult. But with this new tool, show troubleshoot L2 and a MAC address, it's going to go and check your MAC programming in hardware. Or if you do show troubleshoot L3 and the prefix you are troubleshooting, it's going to go and verify the route programming in hardware. Let me show you one example of how to do it. You run a command show troubleshoot L3 and the prefix. The first command it's going to run is show IP route. Then it's going to check show forwarding route and going to make sure the software entry and hardware entry is correct. After that, it's automatically going to run the next command to check the V4 prefix learning history. This command is very useful if you wanted to find out how I was learning this prefix yesterday when I was having a problem. The next command is going to check is the V4 adjacency entry in the V4 host table, grab that adjacency index from there, automatically going to run the next command to check the adjacency in the hardware and make sure they're pointing to the correct interface 147. After that, it's going to run consistency checker, do some more checks, and finally, it's going to declare if the consistency is passed or failed. This is a very useful command, very time-saving. You don't have to know all those commands. Very useful. Remember this. Moving on to our last tool for today's session is iCAM. iCAM stands for Intelligent CAM, Analytics, and Machine Learning. This tool helps us monitor scale utilization and resource utilization on Nexus 9000 switch. It can monitor resources like layer 2 switching, multicast routing table utilization, IP routing table utilization, forwarding information-based TCAM resources, VXLAN scale utilization. To enable this feature, you say feature iCAM, and to start monitoring, you say iCAM monitor scale. Starting with 9.3.5, this tool is automatically enabled. Let me show you how to use this. You run a command show iCAM scale layer 2 switching. Like in this case, someone configured all the VLANs and permitted them on some trunk, open trunk. So it use all the VLANs and you are out of scale here. One more example, show troubleshoot L3 unicast routing, where it shows that routing table utilization, the LPM entries are 91% full. What happens in this case is newly learned route or prefixes will not be programmed properly or they will be misprogrammed, and what you see is either packets getting dropped or they are getting punted to CPU for software switching, which can cause slow forwarding or bad performance. Christian, do you have any example use case to share where iCAM help you in troubleshooting?
So I remember one particular example where a customer wasn't receiving their multicast streams on their end hosts when the Nexus 9K was acting as the rendezvous point. So after checking on the Nexus 9K for a little bit and not making a lot of headway, we thought to check for the scalability using iCAM to see if they were out of scale for some reason with any of their multicast routes. And we found that they actually were overscale for their star comma G routes. And this ended up being a result of an overabundance of SSDP in their network. Once we were able to help them trim down those amount of SSDP routes, we were able to see that the outgoing interface lists for the multicast were being programmed as we would expect, and therefore the receivers were getting the multicast streams as expected. But without a tool like iCAM to help us figure out that they were overscale, it would have been much harder.
Thanks for sharing that. In summary, these are the tools we learned today. We started with Ethanalyzer. It helps us capture the traffic going to and from the CPU of Nexus. The next tool we learn is span to CPU. It's going to help us capture the pass-through traffic. The third tool is ELAM. It helps us capture one packet at a time. Then we learn about consistency checker. It helps us verify the configuration in software and make sure that is pushed down properly to the hardware. Then we learn about show troubleshoot. That command helps us verify MAC table programming or route programming in hardware. And we also learn about iCAM. It helps us verify the scale utilization and resource utilization on Nexus 9000.
I'm sure that all of you have plenty of questions regarding the different tools that we presented today, and maybe even some that we didn't, such as Pi, EEM, local span, ER span, and more. In that case, once our session has concluded, feel free to join us over here where we will be happy to answer any questions you guys may have about troubleshooting tools in NXOS. Or, if you can't meet us right then, join us over at our booth in the data center routing and switching booth in the TAC clinic where we can answer any questions you may have for the remainder of CiscoLive. And if you could, please take a moment to fill out the survey to let us know what you thought about our session. We would greatly appreciate the feedback. And by doing so, you get the opportunity to win some fun and exciting prizes here at CiscoLive Las Vegas.
We want to thank you for attending our session today and patiently listening to us. We hope this session was informative to you, and with this newly learned knowledge, we hope you go beyond.